All right, there we go. Okay, so we were talking about the Ising model. All right, and the Ising model is, again, a model for the magnetization of material as a consequence of the interactions between spins. And so specifically, we had been doing it in one dimension, okay? And in the Hamiltonian for this system, as we've written it many times previously, is minus J sigma I sigma J sum over nearest neighbors minus mu B sum over all spins, like so. Okay, so what we did last time was to solve this, or solve for the statistics of the behavior of the system in the case of no interaction. So with no interaction, that is J equals 0. We solved this thing, and what we showed was that the partition function in particular for n spins, if I remember correctly, was equal to 2 to the n cosh to the n beta mu b. Okay, and then once you have the partition function, you can get the free energy is just, I think there's a beta out here, log z of n. And then what we did was to calculate the average energy. That is the average Hamiltonian. And we did that simply by taking, I believe we did it by log z. So essentially the derivative of the free energy with respect to beta. And what we got, let me make sure I get it correctly here. Where is it? So we got that this was equal to minus n mu b tanh beta mu b. So that's the average energy. And when you look at the Hamiltonian, when you're looking with no interaction, that is, you get rid of this term, then because the Hamiltonian is the energy, and that's related to the sum over all the spins, then you get that this is simply equal to, what did we have? I think it was B times the magnetism. Okay. And so in other words, once you know the average energy, you also know the magnetization. And so our expression for the magnetization that we got was, actually I missed a minus sign there, I believe. So our expression for the magnetization was N mu tanh beta mu b. Okay, and so again, what this thing looks like, we had mu b on this axis, magnetization on this axis. So it goes up to N mu and down to minus N mu. And the tanh function looks like this. There it is. Well, it's a little crappy drawing, but you get the idea. And so in other words, you got a strong negative magnetic field. All the spins align in the negative direction with the magnetic field. You got a strong positive magnetic field. All the spins align in the positive direction with the magnetic field. And then in this region where the magnetic field is weak, the thermal fluctuations start becoming significant. And so the thing smoothly transitions from one extreme to the other. And in particular, when you look at the magnetization here at zero field, so this point here is when B is equal to 0, that shows you that the magnetization at B equals 0 with finite temperature is 0. Okay, so in other words, we ain't explained magnets yet. Now, I think I told you one thing that might have been backwards. So from this, we also wanted to extract the slope of this curve, and the slope is related to the magnetic susceptibility, right? And so the idea with the magnetic susceptibility is that you have a hunk of material, you apply a magnetic field to it, so you apply a B field to it, that gives you some corresponding magnetization. And the magnetic susceptibility is simply the constant of proportionality between the two. That is, it's just, how easy is it to magnetize this material by applying a magnetic field. And so it's defined this way. I think last time I had the opposite. I had B is equal to chi m. You get the idea. All right. And so what this shows is that if you want the magnetic susceptibility, you take the derivative of the magnetization with respect to the magnetic field. Okay, and when we do that, we got something. So if you do that, what you get is actually, I believe, n mu beta 1 minus tanh squared beta mu b. Okay, now the problem with this is that this thing scales with the size of your hunk of material, which doesn't really make any sense. And so to actually get the magnetic susceptibility, what you do is you take this derivative with respect to B, and then you just scale it by the number of particles that you have to give you something that's independent of the size of the material. But you get the idea. Okay, then we started working on, so that was the case with no interactions, and so the magnetization was simply a result of applying a magnetic field to your material. The next thing we were working on was essentially the opposite case. That is, so we started working on part 2, and that is no external field. Okay, in other words, B is equal to 0. So our Hamiltonian in this case is just minus J sigma I sigma J sum over nearest neighbors. Okay, and you'll recall last time that we had defined our system in such a way that, again, we're looking at spins on a line. And this is spin 1, spin 2, all the way to the last spin in. And in particular, we suggested that we were going to work with free end boundary conditions. Okay, so in other words, exactly the way that I've drawn it here. This is the first spin, and there's nothing to the left of it. And N is the last spin, and there's nothing to the right of it. So this is our system. Okay, so when you write out the Hamiltonian, you just write out the sum explicitly. You get minus J sigma 1, sigma 2, plus sigma 2, sigma 3, plus sigma 3, sigma 4, plus sigma n minus 1, sigma n. All right, now the way that we were going to solve this thing was through a change of variables. All right, so our variables currently are our set of spins. And the variables we were going to change into were these variables we called P, P2, P3, all the way up to Pn. And the way that we defined P was simply, so P2, for example, is simply defined to be sigma 1, sigma 2. P3 is sigma 2, sigma 3, etc. Okay? And so now we pointed out that if sigma 1 and sigma 2, or whatever two spins you're talking about, so let's do this more correctly, shall we? So sigma I and sigma I plus 1. If these two spins are the same, plus 1 and plus 1, then P I plus 1 is equal to plus 1. If they are both negative, then you also get plus 1. Okay? It's only if the spins switch, going from the first one to the second one, that is, you have either plus 1 going to minus 1 or vice versa. It's only in that case that this P variable is negative 1. So in other words, the P variable is telling you whether or not the spins are switching as you move from I to I plus 1. Okay, so now I think this was essentially where we stopped last time, and I said we were going to stop like a minute ahead of time because I didn't have time to sufficiently flesh out one of the subtleties of this. And so you can already, looking right here, you can see what this subtlety is, all right? So you can see that there are only two possible values of P. So P can only be equal to +1 or -1. But you can see that for each of those values, there are two possible spin configurations that'll give it to you, all right? So for one value of P, there's two possible states of sigma that will give you that one value. So for +1, they can either be both up or both down. And for -1, they can either be like this or they can be like this. All right. So the thing to keep in mind here is that each P value corresponds to two possible spin configurations. All right. So now with that, we were able to express our Hamiltonian in terms of these P variables. It's trivial, right? I mean, you just look at this thing that we wrote out here, and you see this is P2, this is P3, this is P4, this is Pn. All right. So our Hamiltonian expressed in terms of these P variables is simply -j times the sum of all Pi's from I equals 2 to n. Okay. So that's our Hamiltonian. Okay, so now I think this really literally is where we left off on Wednesday. So now we're going to start doing new stuff. Okay, so if this is our Hamiltonian, then we take that to, determine the statistics of our system. We take this Hamiltonian and we stick it into the exponential Boltzmann weight in order to calculate the partition function. All right, so let's calculate from this Hamiltonian, let's calculate the partition function for n spins. And this is simply sum over, so if we just start from the beginning, it's e to the minus beta h, where the h is a function of the spins, whatever spin configuration you have. Except now what we've done is instead of writing it explicitly in terms of the spin, we're writing it in terms of these p's. Okay, so in other words, I will write this as sum over all possible P configurations of e to the beta, and then I'm just going to stick in what my Hamiltonian is, all right? So it's j times P2 plus P3 plus P4 plus plus Pn. Okay, and so now again in the exponent we have a sum of things. A sum of exponents is the same as a product of exponentials. So this is the same thing as this. Sum over all possible p values, e to the beta jp2, e to the beta jp3, e to the beta jpn. Okay, so now this I can write as sum over spins product from I equals 2 to n e to the beta jpi. So, all right, but I've missed something. What have I missed? Going from summing over spin states to p variables, we've missed this thing. Okay, so in other words, because there are two spin configurations that correspond to each possible value of p, that means that when we switch our variables from sigma to p here in this sum, when we were summing over spins, we had a certain number of terms. And now if we just sum over p's, we're going to have essentially half as many, right? And so what we need to do is to take what we have here and just multiply by 2, right? Because every p variable corresponds to two possible spin states. And so I'm just going to take this thing and just throw it 2 in there, all right? So probably that 2 should have showed up, I believe, back there. But once we got it, that's what we care about. All right, so is everybody good? All right. Okay, so now what we have is a series of terms, each of which, has just one p variable in it, right? So the first term in this product is going to be just p1. The second term is going to be P2, and so on and so forth. And we're going to have n of these terms. And now, again, because each individual term does not have any combination of these p's, that essentially means that the thing is easy to factor. Okay, in other words, the order that I do either the multiplication or the sum in, it doesn't matter. I can switch these freely. I'll get the same result. Okay, so now what I'm going to do is simply switch the order in which I do the sum and the product. So I get 2 product from I equals 2 to n. Sum from my pi equals plus or minus 1 e to the beta j pi. So, all right, cool. All right, so now again, p can be equal to either plus or minus 1. That's it. So then you just substitute that in and see what you get. Okay, so what we get is 2 product I equals 2 to n. And then we just do it. So you get e to the beta j times plus 1 plus e to the beta j minus 1. Okay, so in other words, we can get rid of that, we can get rid of that, and we can just put a minus sign there. Well, hell, this looks exactly like what we got the last time, right? I mean, so this is our old buddy, the hyperbolic cosine again, right? So this is 2 product from I equals 2 to n, and then this thing, this here is just 2 cosh beta j. Okay, so you can see the answer that we get is more or less up to a factor of up to a power, well, more or less it's exactly the same thing that we got last time, just the argument of the cosh is a function of j instead of b, right? Okay, and so if we write this thing out explicitly, what we're going to get is 2 times, and so now another little subtlety here is that our product here starts from 2 to n. Okay, so in other words, when we write out this product, we're only going to get n minus 1 terms instead of n. And this is actually a consequence of our free n boundary conditions, right? So what's happening here is that we start with this spin, okay? And so in other words, this first spin doesn't have anybody next to it in order to interact with. And so because of that loss of an interaction due to the free n boundary conditions, essentially we lose a term in our product compared to our previous result, but otherwise it's more or less exactly the same. All right, so we get 2 times 2 to the n minus 1 times cosh to the n minus 1 beta j. Okay, so this is 2 to the n cosh to the n minus 1 beta j. That is our partition function. So it's exactly the same damn thing, right? We're gonna work through it. We're gonna get exactly the same answer again as we did previously. We're gonna get that the average energy is a hyperbolic tangent. The only difference is this constant out front that we get, this is going to be n minus 1. And again, that's just because of our choice of boundary conditions. And the only other difference is that the argument of our tanh is mu j instead of mu b, right? Which makes sense because, I mean, there is no b. But otherwise, it's exactly the spins either want to line up this way or they want to line up this way, depending upon the strength of the interaction. And when the interaction is weak, then you know it does exactly this same thing again. Okay. So that's it. So 0 external field, or excuse me, 0 interaction. You get one result that looks like this tanh. 0 external field, only interaction. You get the same result. You get the same thing. The only difference is that the argument is mu j instead of beta mu b, or beta mu j instead of beta, or beta j instead of beta mu b. Otherwise, the behavior is exactly identical. All right, very good. So now we've seen what happens when you have no interactions. We just saw what happens when you have no external field. It's pretty much the same thing you get with no interactions. And so now you ask, can't we do this problem in general? What if we have both interactions and an external field? And the answer is, yeah, we can do that. All right, so let's do it. Generalizing model. That is when both J and B are not equal to 0. And so in this case, our Hamiltonian is what we had written previously. It's this. Minus mu B sum over I. So now that's the Hamiltonian that we got to deal with. All right, so now this is going to be a little bit more hairy than the previous two, because the previous two were simplified by the fact that you only had to deal with one of these terms. But now if you're going to deal with both of them, things get a little nastier. And so now it turns out that the best way to do this is in terms of matrices. All right, so let's do this in terms of matrices. Before we do that, I want to remind us of a couple ways to express matrices. All right, so a matrix, so let's say we got a matrix A. That's just a collection of elements that look like this: A11, A12, A1 M, and A21, A22, down to A2N, A N M. Oh, I did that wrong. N1. That's what it's supposed to be. Okay, so a matrix is just a collection of elements like this. Okay, and so now in particular, what I want to do is make sure that we know how to express a product of matrices. All right, so if I take two matrices, A and B, and I multiply them together, then let's say, you know, for the sake of simplicity, let's look at 2 by 2 matrix. So that's A11, A12, A21, A22. And B is B11, B12, B21, B22. Okay, now when you multiply these two things together, what you do is, so like for example, our product matrix, we're going to get some element right here. And to get what that element is, what you do is you start here with this guy, and you start here with this guy, and you work your way this way with this matrix, and you work your way down this way with that matrix. All right. So for example, this term up here is A11, B11. So that's the product of this guy and this guy, right? And then that's plus the product of this guy and this guy, A12, B21. Okay, similarly, if we look at this guy, okay, so what we do is we start with A21 and multiply by that one. So it's B11 plus, and then we, again, go this way and we go this way. So that is A22, B21, so on and so forth. Okay, so now I just wanted to write that out explicitly, just to point out that if we write this in terms of, so you can see what we have here are sums, right? And so way you go, you do this way, you sum over going multiplying the elements going like this. Okay, and the way that you can express this is that you can see that in this first element, this number is staying the same, and this number is staying the same. And what you're doing is you're essentially iterating this first index, okay? So in other words, another way to express this is like this. If I indicate my element is Aij, then the product of two matrices you would write like this. Sum over K. So in other words, if I say that this is equal to a third matrix C, then Cij is equal to this. It's Aik times Bkj, where you sum over K. Okay, so I just wanted to make sure that we're all relatively comfortable with that. So that is how you write down the elements of a product matrix in terms of the two elements that you're multiplying together to get it, is like this sum. Okay, now I want to introduce one more matrix operation to you that you may or may not have seen before, and that is what's referred to as the trace. Okay, so again, if I have a matrix A, whatever that looks like, then I can, again, do what's called the trace of that matrix. And all the trace is simply the sum of the elements along the diagonal. Okay, so in other words, this is just A11 plus A22 plus A33 plus da 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 down to AMN. Okay, so in other words, all I'm doing is I'm just summing all the elements along the diagonal. Okay, so that's the definition of a trace. It's just the sum along the diagonal. All right, everybody good? Good. Okay. All right, so now with that in mind, those two things in mind, let us now try to formulate our Hamiltonian for the general Ising model in terms of matrices. Okay? And specifically, what I'm going to do is to define the following matrix. And I'm going to call this matrix P. Okay? And to keep it simple, let's first of all define this matrix just thinking about a system with only two spins. So in other words, my Hamiltonian in this case is just this. I've just got two spins right next to one another. This is spin 1 and this is spin 2. All right, now the way that I'm going to formulate this matrix for these two spin elements is, actually let me do two colors because that would be more gooder. Okay, so this is sigma 2 and sigma 1 is in red. All right, so what I'm going to do is if I have two spins that are right next to one another, I'm going to define this matrix such that the different rows correspond to the different possible values of sigma 1, and the different columns correspond to different possible values of sigma 2. Okay, so the way to think about this is I have, say, sigma 2 is equal to +1 and sigma 2 is equal to -1 here. And I have sigma 1 is equal to +1 here and sigma 1 is equal to -1 here. And then what I'm going to put as my matrix elements is exponentials of e to the minus what I'm going to call h++. So that's going to correspond to or some variation on the Hamiltonian where both of the spins are up. And here is going to be h to the minus beta h plus minus. That corresponds to this possible configuration. And in this one, it's going to be the opposite. It's h minus plus. So you can see I got minus and plus. So that's this. And this element is going to be e to the minus beta, you can guess, minus minus. That's when they're both down. Okay, so now you ask, what are these h plus plus things? So let me just write them down for you. Okay, so what I am defining as h plus plus, for example, is this. It's minus j, where both of the spins are up. And then so that's just exactly writing down, this, right? Now I'm going to make a little bit of a change to what that term looks like. Okay, so what I'm going to write for that term is it's minus mu b plus 1 because that's sigma 1 is up. But then I'm going to stick an extra factor of a half here. Okay, and then I'm going to do the same thing for spin 2. So it's minus a half mu b plus 1. Okay, so that's how I define h plus plus. Similarly, h minus minus is the same thing. It's just both spins are negative in this case. Whoops. Minus a half mu b minus 1 minus a half mu b minus 1. Same thing. So now you can see there's a pattern here, right? So now h plus minus is defined to be minus j plus 1 minus 1 minus 1/2 mu b plus 1 minus 1/2 mu b minus 1. And finally, just to be thorough, this is this. All right, cool. All right, so in other words, in general, what I have is a matrix P whose elements are labeled by the possible values of my two spins, sigma 1 and sigma 2. Okay, and each element is equal to this, e to the beta j sigma 1 sigma 2 plus mu b over 2 sigma 1 plus mu b over 2 sigma 2. So this is the definition of my P matrix elements. Okay, does that make sense? Okay, so now we know what the possible values of sigma 1 and sigma 2 are. They're just plus or minus 1. So if we just plug in the possible values of sigma 1 and sigma 2, what you get for your P matrix is this. So P is equal to e to the beta j plus mu b, e to the minus beta j, e to the minus beta j, e to the beta j minus mu b. Okay, so that is our P matrix. Notice one thing about this. It is symmetric. Okay, so in other words, this is the diagonal. And what a symmetric matrix means is that the elements that are off the diagonal, specifically this and this, are the same. Okay, so the off diagonal elements of this matrix are the same. That means that the P matrix is symmetric. Okay, so now you say, okay, fine. I've got this P matrix. What the hell is it? Or well, why did I do this? Okay, and let me show you why we did this. Again, let us consider a system that only has two spins in it. Okay. So for a system of two spins, of only two spins, consider the following. Okay, so what I'm going to do is I got two spins. I'm going to take P times P. In other words, for each spin, I'm going to put down a P matrix. And then let's take the trace of this thing. And let's see what we get, shall we? We shall. All right, so let me write it like this. All right, so we're going to take P times P. And like I just showed you previously, when I showed you up here, right here, the way that you write this in terms of the elements is like this, right? So it's the first matrix IK times the second matrix KJ, and then you sum over K. All right, so let's write that out. So let me write it like this. Well, no, let me not get fancy. PIK times PKJ summed over K. Okay, now what we want to do is take the trace of this thing. So let's take the trace. Okay, so the trace is where you just take the first index and the second index and you make them the same, and then you just sum over all possible values, right? So if we go back here, you can see that what's happening is that the first index and the second index are the same, and then you just sum over all possible values of that index. Okay, so in other words, a way to write this is sum over I, sum over K, PIK, PKI. Like that. So that is taking the trace of this product of two P matrices. Now, it doesn't matter what you call these indices, right? I mean, the I, K, J, those are just names. So you can call them whatever the hell you want. So allow me to give them some rather suggestive names, shall we? So instead of calling them I and K, let me call them the following. Call them sigma 1, sigma 2. Okay, so we got P, sigma 1, sigma 2, P, sigma 2, sigma 1. Okay, so that's exactly the same thing. I just renamed what my indices are called, right? Okay, so now let's write out what this is. Okay, so I'm just going to write these two sums. I'm just going to write this as you sum over both sigma 1 and sigma 2. Okay, P1. So I can write this. Let me again make use of the fact that I have colors here. So this I will write as e to the beta j sigma 1 sigma 2 plus mu b over 2 sigma 1 plus mu b over 2 sigma 2. So that's my first P matrix. And this one is exactly the same thing. I just switch what I'm calling sigma 1 and sigma 2. And oh, God. Watch this, watch this, watch this, folks. Oh, damn. Technology, am I right? Check it out. That's fabulous. Okay, so now I write out this second matrix, and that's just e to the beta. It's the same thing. It's just e to the beta, then j, and then I just have the labels switched. There it is. Okay, and maybe you recognize that if you multiply all this out, okay, what you're going to get is the following. Plus j sigma 1, and then these two terms are going to combine to just give you a factor of mu b sigma 1, and then these are going to give you plus mu b sigma 2. It's so in other words, what this thing is, this is e to the beta h. In other words, this is the partition function. Okay, so this is the partition function for two spins. Okay, so in other words, to get the partition function for two spins, what you do is you take two P matrices, you multiply them together, and you take the trace. Okay. Two. Similar, if you wanted to get 3, what you do is trace of P cubed. And then perhaps you can see the generalization coming here. Z of n spins is trace P to the n. All right, so this is our trick that we're going to use. All right, so now the problem is that P is kind of a mess. P is this thing. And you got to take a product of n factors of these things to get what the general partition function looks like. All right, but now it turns out we can take advantage of some of the cool properties of matrices. So now let's refresh our memory of some matrix properties. Okay, the first thing is P, as I pointed out previously, is symmetric. It's also real. It's not doesn't have any imaginary numbers in it. Now it turns out that if you have a real symmetric matrix, it is always possible to diagonalize that real symmetric matrix. So every real symmetric matrix P can be diagonalized. Okay, and when you diagonalize it, you get a resulting diagonal matrix that I'm going to call D. Okay, and the way that you get this is through what's called a similarity transformation. All right, so P is equal to D, and then the way that you get from P to D is that you multiply by another matrix called U in the following fashion. So you multiply by D on both sides by U and the transpose of U. And this, the reason you call it U is that U is unitary. Okay, specifically what that means is that U times U transpose is equal to the identity matrix. That is the definition of unitarity. Okay, so for example, if I start out with some matrix P, and then that is 2 by 2, okay, so for a 2 by 2 matrix P, I'm going to get a 2 by 2 diagonal matrix, or I can get a 2 by 2 diagonal matrix. This will give me a 2 by 2 diagonal matrix D that is equal to this. That is the definition of a diagonal matrix. And when you do this, when you diagonalize this thing, these values are what are referred to as the eigenvalues of your matrix P. Okay, so in other words, this is equal to what I'm going to call lambda plus and lambda minus, the two eigenvalues of P. Okay, where lambda plus minus are the two eigenvalues of P. This is essentially the definition of eigenvalues. All right. So I have a real symmetric matrix P. I can always find a way to diagonalize that matrix using some unitary matrix U. And when I do that, the diagonal matrix that I get out the other side has the eigenvalues of P as its diagonal elements. Okay, so that's one cool property of matrices. The second cool property of matrices is that the matrix, or excuse me, the trace is unchanged by diagonalization. In other words, the trace of P is equal to the trace of D. Again, just a property of the trace. And hey, look at this. If this is D, you can see what the trace is going to give you. The trace is just going to be the sum of eigenvalues. All right, so this is just going to be lambda plus lambda minus, our two eigenvalues of P. Okay. All right, so our two properties are so far are any real symmetric matrix can be diagonalized. If you take the trace of that real symmetric matrix, what you will get is the sum of eigenvalues. Okay, the third property is just, let's note the following feature. So note this. So if I want to take P to the n, that is the same thing as P times P times P times P n times. Now, notice that I said that I can always express P in terms of my diagonal matrix like this. So I'm just going to substitute this in down here. So this is equal to U times D times U transpose times U times D times U transpose. And then I'm going to get that n times. Okay, so this is 1, this is 2, and this is n. Now notice that right here, so in between each of these products, I get a factor of U transpose times U. U transpose times U. And because this matrix is unitary, U transpose times U is just equal to 1. And I guess I should say that explicitly. It's also equal to this. Okay, so in other words, this is the same thing as U times D to the N U transpose. Okay. Finally, if I look at D to the N, that is just lambda plus 0, 0, lambda minus to the N. And because this matrix is diagonal, this is trivial to figure out what it is. This is simply lambda plus to the N, lambda minus to the N. Okay, so in other words, combining all of these cool matrix facts together, what we get is that the trace of P to the N has to be equal to the trace of D to the N, and we know what that is. It's just the eigenvalues of P, or the sum of the eigenvalues of P raised to the nth power. And notice that's our partition function. Whew. All right, so now what we have done is we have changed our problem from how do we find the partition function of this complicated Hamiltonian to find the partition function of our Hamiltonian. All we have to do is to take this P matrix that we defined right here. So this is P. And we just have to find this thing's eigenvalues. In other words, we just have to diagonalize this thing to find its eigenvalues. We know how to do that. So we have reduced the problem to simply finding the eigenvalues of P. So the problem is simplified to diagonalizing P and finding its eigenvalues. I'm going to assume you know how to do that because you guys have taken quantum mechanics before, right? If you've taken quantum mechanics is all about finding it's all about diagonalizing your Hamiltonian and finding its eigenvalue. That's what quantum mechanics is. So if you've taken quantum mechanics, which I believe is a prerequisite for this class, then you know how to find the diagonalization of a matrix and its eigenvalues. Okay, so I'm not going to bore you with the details of how to do this. I'm just going to tell you what the answer is. Okay, so the eigenvalues of P are the following. E to the beta j cosh beta mu b plus or minus sinh squared beta mu b plus e to the minus 4 beta j square root. Okay, so P is 2 by 2, so you should get 2 eigenvalues. This is what they are. So now you can see why I labeled them plus or minus. So the plus eigenvalue corresponds to when you take the plus sign here, and the minus eigenvalue is when you take the minus sign here. All right, so these are our eigenvalues. And by the way, the matrix U, which diagonalizes P, you can find to be this, e to the minus beta j, e to the beta j minus mu b minus lambda plus 1, 1, e to the minus beta j, e to the beta j plus, I believe mu b minus lambda minus. So that's what U looks like. And again, if you've taken quantum mechanics, you know how to get this. All right, so this is the answer. We got the answer. So now we're out of time. And so when we come back on Monday, we're going to take this answer and I'm going to show you what this answer means. All right, so these are our eigenvalues. We take the nth power of these eigenvalues and their sum. That gives us our partition function. And then once we have our partition function, we can find things like magnetization, susceptibilities, and so forth. And so that is what we will do on Mondays. I'll show you how the magnetization behaves. All right, so any questions? All right, very good. So I will then see you guys on Monday. Have a good weekend and stay safe out there, kids. Oh, somebody said something. Amazing. Yes, it was amazing, wasn't it? All right, see you guys.